All right, so in this video, we're going to talk about electric potential and electric potential energy. So this is another way of looking at the same type of phenomena as we did in the previous, lectures. That means we are looking at electric forces exerting some kind of, you know, push and pull on other charged particles generating or creating electric fields in space, and basically all those interactions between charged particles. That means electric fields exert force, then we can use electric field to find the force, and then we can, once you have the force, you can basically predict in terms of position, velocity, and things like that, right? The One of the things we realized in the previous lectures is that electric force, being non-constant force, makes it a little bit difficult to find information about the motion of the particle, because unless the electric field is uniform, electric force is not constant, means acceleration is not constant, so none of the kinematic equations could be used to find velocity or position, you know with this, so like a simple equations, those kinematic equations, right? When we use them, we can't really use them unless we were specifically told that, let's say, electric field is uniform. All right, so there's another way of looking at basically same problems, but instead of using those vector notations, vector fields, vector forces, and things like that, we can use scalar quantities. If you remember, we talked about energy in previous mechanics class, and when we talk about energy, we basically learned how we can solve for example, speed or position, let's say height dependence or shape and things like that, using the energy approach. That means we can calculate this quantity that we call energy for an object, and we can then compare the energy at one point with another point, and if there were, let's say, certain type of forces doing, let's say, transferring energy or doing work, we call them conservative forces, then we could potentially use this energy approach to solve for the speed, even if the, let's say, force was not constant. That means this concept of energy allows us to use scalar quantities, which is the most important thing about, this chapter. Use scalar quantities to solve for a number of things: speed, potential, speed, position, and things like that. Using this, the concept of energy, conservation of energy, and the type of forces that we're dealing with. All right, so let's see then what we have. All right, so this is kind of like, let's say, what we had from the previous chapter, that if there is a source charge, this source charge generates electric field, and if you bring a test charge and place it in that electric field, there's a force acting on it. So there's an electric force. That means, let's say, here's the some kind of, source charge. Okay, and at any point around it, there is then signature of this source charge, right? So there's a vector signature. There's this electric field that it generates. So we could pretty much, simplify, and remember, we can do this electric field lines. And then we said that if I place some kind of test charge right here, this is a test charge, then there's a force acting on this test charge because there's already a field. But that information about the field, well, it's an electric field, it's a vector, and also the force that we calculate is also a vector. So we have to be careful in terms of magnitude and direction and things like that. But you bring a test charge here, and there's a force acting on it. Now, going back to this energy concept, one thing we learned about energy concept is that if there's a force acting on the object and this force changes the position of the object, then we can say that the force does work or did work on this object. So that means we can recall this concept of work. Now, the work was the transfer of energy into the system. So it's a mechanism of transfer of energy into the system if the work done is by a non-conservative force, or mechanism of converting energy from one type to another if the work done by what we call conservative force. That means, equation for the work done, general equation was force that dl going from point, let's say point 1 to point 2. Okay. Now, what we have here is this is the equation for the work done. And work done was a scalar quantity. And work can be done by two types of forces: conservative forces, non conservative forces. All right, so important thing was or a little more useful, let's say the type of work was work done by the conservative forces. Now, the electric force happened to be a conservative force, and which means then when the work is done by conservative force, here's what we have, like here's a change in energy. Change in energy equals the work done by the non-conservative force, which means when the work done is by a non-conservative force, like push, pull, friction, tension, those are non-conservative forces. Energy of the system changes. That means energy at point one is different from energy at point two. Let's say at point one, your energy is 100 joules. At point two, then your energy then 200 joules. What's the difference, or where did the difference come from? Well, it's the work done by the non-conservative force. They transferred energy into the system, and your energy increased. But when there is a work done by the non-conservative force, change in energy equals zero, which means that energy at point one and point two are exactly the same. 100 joules at point one, 100 joules at point two. Then what's the usefulness of the work done by the conservative force if it's not changing the energy? Well, when it's not changing the energy, and which is basically a very useful concept and very useful thing for us to know, work done by conservative forces go into changing the type of energy that we have. They are able to convert one type of energy into a different type of energy, kinetic to potential, potential to kinetic, or let's say into um, internal energy, depending if you're taking internal energy to your system. But the idea here is this: if you have a conservative force doing work, then the total energy of your system remains constant. That's why we call them conservative forces. They conserve energy. And we can then use this, you know, let's say this concept of conservation of energy in this particular electrostatic phenomenon as well. That means when the particles, interacting only through the electric forces, energy is exactly the same at any point of this interaction. That means anytime, at any point, exactly same energy. But there are different type of energies that can be converted from one to another. All right. So you can say, right, to find the work associated with the force, look at an infinitesimal small displacement vector that is oriented tangent to the path through space. So that's what we have in this equation. You can see, right? It's force dot dl. That means we are looking at some kind of length dl. That means, for example, you take this source charge and then you say, all right, so generate electric field. Then you bring a test charge, place it at point one. Well, there's a force acting on it. Now, I didn't really give you the charge of the test particle, test charge. So we don't know exactly technically in which direction is the force. We know that there's a force because the test particle has a charge and there's electric field. But in which direction electric field, that's the thing about this, vectors. In which direction of the electric field depends on the charge of the test particle. If the test particle, for example, is negative, so let's say it's a negative test particle, then the force will be in the opposite direction of electric field, will be in this direction. So this is then the force acting on it. Again, when there's a negative test charge, the force always in the opposite direction of electric field, which also makes sense because if it's a negative particle and the source charge is a positive particle, there's attractive force toward each other. So that's why, for example, you bring a test charge, you place it at point one, there's a force acting to the left for this particular diagram that I have. Now, as it goes from then point one to point two, let's call this some point two over here, then we can see that this force going to make the particle change position. And generally, that's what required for the work done. That means when the particle does work, there has to be a force acting on it, and there has to be like some kind of displacement. And if the force changes the position, which is a displacement, right, of a test particle, then there's a work done, going from point one to point two. Now, if I'm looking at then the energy at point one and comparing to the energy at point two, they're the same. So then, what does the conservative force do? Well, they go into changing then the one type of energy into another type of energy. And generally, when we were talking about conservation of energy, if you remember, we would always represent energy in terms of the sum of kinetic energy and potential energy. And that's what we have. And that's what conservative forces do. They can convert your energy from one type, let's say kinetic, to another, let's say potential. And they can convert them back and forth without changing the total energy of the system. That means energy at point one could be kinetic energy plus potential energy. Those are specifically for point one. And if you go from point one to point two, since energy at point one equals to energy at point two, so you can say that this is equals to the K2 plus U2. And that's basic energy at point two. That means we can say the sum of those two types of energies at point one is exactly same as the sum of those two types of energies at point two. And what work that when the conservative force does work, it converts one type into another. Okay, and that's very important. Let's say information that we can use to relate all of those quantities like electric field, electric force, or find the speed, position, but without actually using the vectors, without using electric field. We can, instead of electric field, we can use some kind of scalar quantity. We're going to talk about that, potential, right? Using, let's say, instead of talking about force pushes and pulls and makes the object have a displacement, we can talk about there was a work done. That's why object went from point one and point two. That means scalar quantity information can be used to calculate pretty much same type of information, but in much simpler way, because it's always easier to work with scalars. All right, but equation for the work done is still this integral. We are looking at the integral, and the important thing to understand here is that technically that integral cannot be simplified, because force that we have between two charged particles, right, electric force, is not constant. So we actually have to do the integral and integrate and find what the work done technically is equals to. All right, so let's look at this derivation. So let's say you have a source charge, let's say, and we know then, let's say, it generates an electric field. So let's say this is the electric field that it generates. And we have a charged particle right here, so Q naught. And we're going to call this point one. And I'm going to have like, okay, so it goes from point one to, let's say here, point two. That means this is the displacement. So then work done, since there is going to be an electric, let's say, electric force acting in this direction. So let's say this is the electric force. Because there's electric field, you place a test charge over there at point one, there's electric force. Now let's say this is a negative charge, so electric force is in the opposite direction of the electric field. That means the force, electric force, is going to make the object go from point one to point two. All right, so here's what I have. The work done is equals to integral of F dot dl, that was a dot product, going from point one to point two. Now, generally what we have is this. If the force is constant, you can take it out of the integral. So this becomes force dl, which becomes then force delta x, which is simple enough if the force is constant. Well, we can't use it like this because electric force is not constant. It's path dependent, because those two particles, let's say right now, are one distance apart, but when q2, this q naught gets here, then there will be r2 distance apart, and we know that force is going to be different. So then what I can do here is I can say, all right, so I can't remove that. So this becomes, that means that you just choose like a small infinitesimal, like, small dl, and then just basically work with that. So this is then equals to, all right, so since we cannot remove that, That means we have to work with that. What is electric force? Well, it's K, source charge, then times the test charge divided by separation between them squared. That means that anytime that's the expression for the electric force. Well, if this is then the equation for the electric force, then so this is the Fe, right? Then this is I'm gonna replace dl with just dr. Okay, so the just dl just dr, which is same thing, just a length element. That means k q naught can come out technically in this particular case, because what we have here is those three quantities, right, are constant. Then I have integral going from 1 to 2, 1 over r squared dr. All right, so if I'm then calculating this, so I'm going to get k q naught, and then 1 over r squared is then negative 1 over r. That means if I integrate that, 1 over r squared is negative 1 over r, going from 0.1, let me put like r1 to r2, like that. That means what I get here is this, then k q naught, then 1 over, if I kind of rearrange, becomes 1 over r1 minus 1 over r2. Okay, that means, again, let's see what we have. Work done is equals to k q naught over r1 minus k q naught over r2. If I kind of change, remove that, the negative sign, it will be like this: negative k q naught over r2 minus k q naught over r1. So putting that negative over there. Now what I have here is this expression over there is an expression of k q naught over r, is expression of electric potential energy. Electric potential energy. And this is then represents electric potential energy of 0.2 minus then electric potential energy of 0.1. That means what I have is this: work done by then the electric force is equals to negative of change in electric potential energy. That means we have new type of potential energy, which is electric potential energy. Remember, potential energy is a stored energy that can be used, by other forces to convert from potential to kinetic, right? And that's what electric force pretty much does. Electric force can be used to convert a potential energy into kinetic energy. And one thing, hopefully, you can remember from the mechanics class is that when there's a work done by the conservative forces, one of the important things that they do, they always change the potential energy. That means work done by conservative forces will always be, proportional to some kind of change in potential energy. But there's a negative sign which indicates that work done by the conservative force equals negative of change in potential energy. And this is true for work done by other conservative forces. Now, let's talk about conservative forces. There are two conservative forces you learn in your mechanics class. That's the gravitational force and then elastic, or let me put like spring force. And now a new type of conservative force, and that's the electric force. So when the gravity is doing work, remember, gravity can also affect potential energy of the system. But that potential energy was the gravitational potential energy, which was then mgh. When the spring force is acting, it also can be used to change the potential energy of the system. That means conservative forces are responsible for the potential energy of the system. Spring force gave us spring potential energy, which was 1/2 kx squared. And now we have electric potential energy due to the electric force, and then electric potential energy, then k q naught over r. That means you have three types of potential energies right now: gravitational, spring potential, and electric. One thing we have here is that gravitational technically is one of the examples where the force is always constant, because Gravity, right, mg, right, that's magnitude of the gravitational force, pretty much never changes. Spring force was a variable force, so this you can see, right, potential energy, you know, had to be, integrated in order to get the spring potential energy. Same thing with the electric force. So we had to integrate to get that expression. But the idea here is this: whenever the force, conservative force doing work, they always change the potential energy of the system. Okay. Now, general there was a general theory of the work kinetic energy. We call it work kinetic energy theorem, which says that whenever there's a work done on the system, it goes into changing kinetic energy. That means all the forces, whenever they're doing work, they change the kinetic energy of the system. But when the conservative force doing work, they also change the potential energy of the system. That means work done by conservative force equals delta K, but it will also equals to negative delta U. Then if I put them together, becomes delta K plus delta U. If I move this to the other side, then equals 0. And that's the equation for the conservation of energy, okay? Which means that K1 plus U1 is equals to K2 plus U2. Total energy at one point is exactly the same as total energy at another point, where the energy is the sum of those two types of energies. All right. Now, kinetic energy, if you hopefully remember, it's 1/2 times mass times speed square. And one important thing about this is that when I'm using this equation over here, again, as I said, it doesn't matter if the force is variable. Also, conservative forces are the type of forces when they're doing work, the work done is independent of the path taken. So let me very quickly give you gravitational potential energy, sort of like, let's say, review, because in a way there's a lot of similarities. So for example, let's say this is Earth and you're holding an object here that has mass m. Well, one thing we know here is that we would say that, all right, so there's a potential energy. Okay, there's a potential energy. Why? Because we take the position of Earth to be 0, like the ground to be 0. And then let's say if this is 0.1 and this is 0.2, then we can say position of 2 equals 0. We always want some kind of reference position. Then we can say then position of 1 then is equal to some h. Okay. Then if we let go of the object of mass m, it's going to, fall down. When it's falling down, the force acting on it is gravitational force. Okay, it's a gravitational force. And then one thing we have here is that it's going down like this. That's our displacement. Now, one of the things we have here is this. If I'm looking at the potential energy of 0.1, this will be mg times h. Since h is not 0, and it's, let's say, I'm taking up to be my positive y direction, so then this is my potential energy. Obviously, it's a positive potential energy, right? Because it's above my reference position, which is 0. But then what is the potential energy of 0.2? Well, it's mg times y2, but since position 2 is 0, so just no potential energy there. Okay. Again, I don't necessarily have to take ground to be 0, but the idea here is this. It's easier to take one point to be a reference point and then have that to be equals to 0, because gravitational potential energy, okay, so this is just a gravitational potential energy, is height dependent. And in this case, higher the altitude, more the potential energy. Okay. That means, for example, we have 100 joules. That's the gravitational potential energy. That means gravitational potential energy at 0.1 is 100, at 0.2 is 0. When object of mass m going from 0.1 to 0.2, right? One thing we have here is then potential energy decreases, right? Because it's 100 here, well, as it's going down, potential energy decreases. Because let's say I choose some 0.3 over here, which is somewhere in between. Well, one thing I can see that potential energy of 0.3 is mg times, I don't know, let's say y3, position 3, right? And I can see that, it's if it's halfway, then since it's mg times h and h is half of it, then this will be half of potential energy at point 1, which will be, let's say, 50 joules. And as you can see, right, if you go half of that, it's going to decrease, decrease, decrease until it's eventually 0 at point 2. That means potential energy decreases. So if I'm looking at delta U going from U2 minus U1, well, this is going to be negative quantity, because this is like a 0 minus 100 joules. I get negative 100 joules. Well, then how about the work done by this, gravitational force? Is it positive or is it negative? Well, work done, remember, you are looking at in terms of general equation is going from point 1 to point 2 f dl, f dot dl. But remember, dot product is what? Dot product is, is f dl, then cosine of theta. And the theta is angle between the force and displacement vectors. Well, if the force and displacement both in the same direction, then cosine of theta is 1, because theta is 0. That means my work done here is a positive quantity. Well, that means when work done, by a conservative force is positive, potential energy then is a negative, or change in potential energy, sorry. When work done is positive, potential energy, change in potential energy is negative. Same way if you go sort of like other way around. If you go from the ground, which is my point 1, to some position 2, if I take ground still to be my reference, it's equals to 0. My potential energy is mgy1. That's going to be 0 because my y1 is 0. Now, going from point 1 to point 2, my displacement is like this, delta y. Well, but the entire time as the object is going up, well, the gravitational force is still acting in the opposite direction. But as I go to point 2, my potential energy, mgy2, which is lesser than mgh, is going to be higher, right? So u2 is greater than u1. That means delta u is now a positive quantity. Delta u is positive, but then the work done by the gravitational force is going to be negative. So this is, you can see, right, why work done by a conservative force is equal to negative delta U. Because when this is positive, that's negative. When this is negative, this is positive. And that negative indicates that those, exact, differences between them. They always have opposite sign. When the work done by gravity is positive, potential energy decreases. When work done by gravity is negative, like in this case, potential energy increases. All right, so it's easy to see it from this gravitational potential energy point of view. But that's also same true for the electric, potential energy. That means when the work is done by electric force, this will always go into changing potential energy, but such that potential energy will always decrease when the work done is positive, or increase when the work done is negative. That's why, in a way, this is negative. All right, so let me change this. So it's negative you let's say potential at point 2 minus potential at point 1, or if I move the negative inside, becomes potential at point 1 minus potential at point 2. So that's generally how you can write work done by the electric force. Okay, so this is then the equation for the electric force. Now, one thing we can do here is then this, right? So remember, we started with this, work done is equals to then the integral of f dot dl. Okay, now then what I'm saying here is this. So this is the equation for the work done, and this is work done by the electric force. Now I'm saying also that since work done is equals to integral of f dot dl, going from point 1 to point 2, it also equals to then negative delta u. Well, let's say I move this negative to the other side, then I can say then delta u is equals to negative f dot dl. That means this is then how I can represent change in potential energy due to this electric force. That means, again, delta u, which is u2 minus u1, in the equals to the negative integral going from point 1 to point 2 f dot dl. So this is what we have. Now, I can also rewrite this equation in terms of then negative integral. Remember, what's the equation for the electric force in terms of electric, electric field? This is then test charge times electric field, dot dl. I can also write it in terms of this. That means it's negative q naught integral going from point 1 to point 2 E dot dl. That means I can represent potential energy due to the, due to the fact that there's a charge, test charge particle, right, in the region when there's a electric field. Okay. Which should make sense, right? Because as I said, right, if there's a source charge and this source charge generates, let's say, this electric field, when you place a particle, test particle, right, at this point 1, right, you place this, particle at this point 1, then there's going to be force acting on it. And this force will always move this test charge from some point 1 to point 2, depending on it. So it can, if let's say if this guy here is positive, it's going to make it move from point 1 to point 2 over here because force is going to be in this direction. Okay. But still, there's going to be displacement as soon as you put that. So that's why you can see, right? If there's electric field, you bring this test charge particle there, its potential energy will change. Because its potential energy at point 1 is equals to k q q naught over r1, and this is being r1. So you can say, right, this is the potential energy when q naught is placed at point 1. But because there's going to be force acting on it and there's going to be displacement, potential energy will change to different value, because then it's going to be k q q naught over r2. And let's say r2 is now different. That means potential energy also will be different. So there's a change in potential energy. Okay. So for this particular case, for example, you can see, right, in terms of, since this is the direction of displacement and force is acting in the direction of the displacement, the work done is positive. Work done is positive means that potential energy delta U should be negative. So delta U should be negative, which should make sense because potential energy at point 1 is greater than potential energy at point 2. Why? Because both are inversely proportional to position. So since R1 is smaller, U1 is bigger. R2 is larger, right? Then U2 is then smaller compared to U1. That means potential energy at point 1 has a higher value because position between charge, let's say test charge and the source charge, are smaller. And because the electric force doing positive work, potential energy will decrease. That means the test charge going from point 1 to point 2 will decrease its potential energy. Now, when you decrease your potential energy, what happens? Well, remember, you can't just decrease potential energy, which means, like, let's say you destroy your potential energy or thing like that. No. What happens here is this. If I'm calculating then energy at point 1 and comparing to the energy at point 2, well, they're going to be the same. Again, because then this work done by the conservative force, which is electric force, right? So what I can say is this: K1 plus U1 equals K2 plus U2. That means I can look at it in terms of change in potential energy, right? Change in potential energy between points 1 and 2 then directly affects kinetic energy at point 1 and point 2. So for example, my total energy is 100 joules before and after, because electric force does not change the total energy of the system. So if I started with 80 joules kinetic potential, which means 20 kinetic, then when I got to point 2, my potential energy decreases. Maybe that means it's down to 50 joules. Well, which means that if I'm losing potential energy, it will then go directly to increasing kinetic energy. That means now my kinetic energy increased to 50, while my potential energy decreased from 80 to 50. Okay, so there's exact equal amount of change. That's why change in kinetic energy plus change in potential energy equals 0. That's a conservation of energy. That means if I had a negative 30 joules, that's how much I lost potential energy, I had the gain of 30 joules for the kinetic, So if we add those two together, you should get zero. This is the conservation of energy. Now, conservative forces convert from one type of energy to the another type of energy. And that's what we have. So if we go back to this slide, right? So this is pretty much what it does. So because, let's say, work done by the electric field, F dot ds, we can replace that in terms of the force, like replaced by the Q naught times E, right? That expression, dot ds. So then we can calculate using that change in potential energy. Okay. That means delta U equals negative Q naught times integral of E dot ds. Again, going point one or point two, point one to point two, or from point A to point B. Pretty much the same thing. So because the force is a conservative, the line integral does not depend on the path taken by the charge, which means it doesn't even matter how the particle goes from point A to point B. So let's say here's point A, here's point B. It can go straight like this, can go like this, can go like that. Doesn't matter. That's the beauty about energy approach. When you're dealing with the conservative forces, it's path independent. All you need to know, what is the energy at point A, what is the energy at point B, and then if the work is done by conservative forces, the energy is exactly the same. So then you can use that to find other things. Like let's say give me position, I can give you the speed, or give me speed, I can tell you the position, and so on and so forth. Those are the things that we can use from the scalar quantity, like potential energy. All right. Now, there's one important quantity as well that we're going to look at it, and that's electric potential, which is not the potential energy, but it's the potential energy per unit test charge. Okay. And we use V for that. That's the potential, sign for potential, symbol for potential. And you can see, right, it's potential energy divided by test particle, test charge. Well, we know what the electric potential energy equation now look like. Like let's say it's K, Q, Q naught over R. Then we divide this by Q naught. Well, you can see if I divide by Q naught, then, well, this Q naught, that Q naught is going to cancel out. And what I get here is I get K, Q over R. What does it mean? Well, it means that the potential is independent of the value of Q naught. And the potential has a value at every point in an electric field. Okay. Which means that potential is another effect of a source charge. That means if I have a source charge, Q, at any point around this source charge, now I can find not only the electric field, but also electric potential, which is only because of the source charge. All right, so again, electric potential is different from electric potential energy. Electric potential is scalar effect of a source charge on the space around it, just like electric field is the vector effect of that source charge. Electric potential energy is amount of energy that you need to use to bring a test charge to some position, P relative to a source charge. That means there are two different informations. They are related though with this equation. Okay. Now, there's that simulation that I used last time. I want to also use that to demonstrate, let's say, what I mean by potential is the effect of the source charge. So I think that simulation right nicely demonstrates that. Let me open it up so I can show you. All right, so what I mean here is, let's say, what I want to show you is this. Let's say we have a empty space. Okay. Remember, if empty space, see if I try to look at the electric field, there's nothing there. And here's, for example, like a voltmeter, something that measures the potential. So if I look at potential, see, I'm not measuring anything. I'm not measuring anything, so it's zero. Okay. Then what I can do here is I place a charge. That's a source charge. And we can see, right, this entire region is filled now with electric fields. Okay. But also, this entire region, then we can think of like, let's say, also filled with some scalar quantities, scalar information, and that's the potential. So if I take this one over here, if I look at, then see, I have now voltage, that sorry, potential, right, in terms of volts. We're going to talk about that the units are volts for the potential, this quantity we call potential. That means this is 2.627 volts. This one is 1.9 volts. This one is 6.8231 volts. This one is 16 volts. You can see, right, closer and closer I get to the charge, higher it is, right? So, and just get very high when I'm, kind of like, let's say, as close as I can. So that means it's also similar to the electric field in a way, right? We could see the equation, right? Is that it's KQ over R. Remember that was the equation, right? KQ over R, which means that closer you are to the source charge, higher the potential. Further you are, lower the potential. And equation, right, only has information about the source charge. That means, so like, let's say if this is the voltage, right? Voltage is basically means that voltage is potential difference. One of the things I can do here is I can, reference this position, right, or this value 2.799 as the potential difference with respect to the, a reference position that I'm going to take. Now I'm going to, when we go back to the, the whiteboard, I'm going to show you, like, let's say, where exactly that reference position should be so that potential is equals to 0. But what we have here is this. Okay. Now, what happens, let's say, if I have a negative charge? So let's say, let's go back and I have a negative charge. Well, remember, difference here is that electric field magnitudes are all going to be the same, but then electric field directions change, right? And now they're pointing all toward the negative charge. Well, what I have here is, by the way, the shaded means that actually, like, let's say, it weakens as you go away from that, charge. One other information here is this. Well, same thing with the potential, right? With the voltage. By the way, voltage is a potential difference. Potential is sort of like, let's say, potential at exactly some specific position. So now, if I'm going to take now the voltmeter, I'm going to measure, see what you get. You get negative numbers, which means that if your source charge is negative, then your potential everywhere around it is negative. Again, still, it's, let's say you can higher and higher negative, but remember that's technically lower and lower, right? Because when you talk about scalar quantity, negative 32 is smaller than negative 4, which is then smaller than negative 2, which is smaller than, let's say, negative 1, because this is a number, right? Scalar number. So that means this is considered to be higher potential, and this is considered to be lower potential. Okay, that means you go from higher to lower. Now, very important thing we're going to talk about this as well is this. So remember, if this is a higher number than this one, because let's say negative 1.9 is a higher number, larger number than negative 6. So see what we're doing. This is a larger number. Then if I travel in the direction of the electric field, my number decreases, decreases, decreases. That means if I'm traveling in the direction of electric field, potential decreases. This is also true if I have a positive source charge. So see, here's my potential, 12.37. And if I'm going in the direction of electric field, my potential actually decreases. If I'm going in the opposite direction of electric field, my potential actually increases. And that's a very important thing that we're going to use to derive the expression that relates electric field and potential. That means if you go in the direction of electric field, your potential decreases. If you go in the opposite direction of electric field, your potential increases. All right. So let's go back now to the slides. And that's what we have. So you can see, right, electric potential is a scalar quantity, and delta V, which is change in potential, potential difference. This is what we technically call voltage. Voltage is a potential difference, equals then change in potential energy per unit test charge. And you can see, right, then delta V is equal to the negative of integral E dot D, well, DL or DS, same thing. Now, why is this equation? Well, remember, we had this equation, right, where changing potential energy was equals to negative Q naught integral of E dot ds. going from point A to point B. But what I'm doing here, I'm now replacing potential energy. See, if I move the Q naught over there, this becomes delta U is equals to Q naught times delta V. This is how potential energy related to the potential. Okay, delta U equals Q naught times delta V. So if I replace this delta U with Q naught times delta V, then those Q naughts cancel out from both sides. Again, when you're considering potential, you don't really need any information about test charge. Only when you have a potential energy, you need the test charge information. For the potential, you don't need. Potential relates to quantities that only dependent on the source charge. Potential, which is the scalar information about the source charge, related to the vector information about source charge. And that's the equation where the delta V equals the negative of integral of E dot ds. All right, so just as the potential energy, only differences in electric potential are meaningful. And that's also important to remember that energy at point one or energy at point two, not really that important. What's important is change between them. How did they change? Did you increase? Did you decrease? Because if I tell you, okay, so potential energy is 500 joules at point one, what will it really tell you about, what happens to the object? Nothing. But if I tell you that if it goes from point one and point two and potential energy increases, then you already know some important information. Because if you're going from point one and point two and potential energy increases, well, that increase will come because of then the kinetic energy had decreased. Remember, you cannot have increase in one thing without decrease in another thing. This is all going to be in terms of kinetic and potential. If potential increases, that's because kinetic decreased. Or if you go from point one and point two, and you know that, let's say, objects slow down, well, slow down means kinetic decreased, which means again potential increased. That means change between point one and two. That change, right? That delta U gives you information, where the information at some specific point doesn't really help you with, you know, with figuring out, the calculations. All right, so we often take the value of the potential to be zero at some convenient point in the field. Now, which one is that convenient point? Well, let's look at over here. Remember, the equation for the potential was this: K Q over R. That means if you have a source charge, let's say here's a source charge, at some point P, which is a distance R from this source charge, here's how you calculate the potential. Now, remember what we talked about, right? This potential, this potential is if the charge is the source charge, right? If this is positive, then potential is positive. So let's say I calculate 20 volts, plus 20 volts. Well, remember, what is the electric field due to the source charge? Well, because it's positive, electric field is going to be radially away from it. Now, what happens if you consider a point that goes, you know, in the direction of the electric field? Well, remember what we talked about, right? If it goes in the direction of electric field, potential will decrease. So it will be 20, 18, 17, so on and so forth. So it's going to start decreasing. That means if I continue following the electric field, my potential decreases until at some point it's zero. Now, where is zero? Well, it's a very simple calculation. V is equals to KQ over R. Under which condition V is zero? Well, it's zero when, okay, so right, KQ over R equals zero only when R is equals to infinity, right? KQ divided by infinity will give you zero. That means one thing you can do, right? If you rearrange, right, KQ over zero, that's where, you can see that it's undefined. That means infinitely far away, at some point, potential is then zero. So that's why when a lot of times I can say that changing potential is when you have V2 minus V1, and let's taking that point one to be infinitely far away, so it's in infinity, then becomes V2 minus zero. So all I have to do is just calculate the potential at this point P, and I have my change in potential, because my reference point is infinitely far away and potential is zero there. All right, so that's pretty much what we have. So the potential is characteristics of the field only. It is independent of the charge placed in the field, that means it's completely doesn't care about what type of test charge we're using. Potential only depends on the source charge. That means even if I don't have any test charges, I can look at any random point P and calculate the potential there, because this potential at that point P only depends on the source charge. Okay. Now the difference in potential is proportional to the difference in potential energy. Now, what is this then? What's the usefulness of potential, you know, let's say in terms of the potential energy? Well, here's the thing. If I'm then saying, all right, so here's then the change in potential energy, referencing like infinity. And let's say delta V equals like 20 volts. Well, if I know my change in potential at that point P, that means relative to the infinity, that point P has a change in potential of 20 volts. Now, when I bring a test charge at that point P, and I want to know, okay, so then how much potential energy did this test charge gain or lost when it came to this point P from infinity? All I have to do is just use this equation. Delta U is equals to Q naught times delta V, because I already have the delta V over there. And if this test charge, I don't know, let's say is 5 nanocoulomb, so it's just 5 nanocoulomb times 20 volts. So it becomes 20, 100, right? 100 nano coulomb times volt basically gives you joules. All right. So if this guy is positive and potential was positive, that means there was a gain of 100 nanojoules to bring that positive test charge particle from infinity to that point P, which makes sense, right? Because if this is positive and this is positive, it will never on its own come to this point P. The field is in that direction. And then we were bringing this opposite to the direction of the field. Force was doing a negative work because force at all times acting in this direction. That means work is doing, this field or force is doing negative work, which means the potential energy would always increase. And that's what we do. If I know then the potential at some point, this equation then can tell me change in potential energy. Okay. That's why potential energy is characteristic of the charge field system. Okay. Due to an interaction between the field and a charged particle placed in the field. To find my delta U, I need this guy. Without this guy, I'm not going to find, any information about potential energy. Because what I'm technically calculating with the delta U is how much potential energy did this test charge gained or lost, or my system, right, when I brought that charged particle here at that point P. All right. So the electric potential at any arbitrary point due to a source charge equal to the work required by an external agent to bring the test charge from infinity to that point divided by the charge of the test particle. And that's what we have. So work done by a non-conservative force equals then delta U, which is then Q times delta V, which is exactly opposite of the work done by the conservative force. That means if I'm saying that work done by conservative force equals negative Q times delta, Q naught times delta V, then when I'm doing work on the charge, when somebody pushes the charge, not the electric field, but some kind of non-conservative force, then work done is equals Q times delta V. So that's kind of what we have to do. We have to understand that. So technically there are two equations, right? Work done equal by a conservative force equals negative delta U or negative Q times delta V. But if the work done is by, some kind of external agent, so then it equals to Q times delta V. So you have to be careful. Is the work done by external agent or is the work done by the, by the field? Okay. So technically you want to look at it in terms of, was the work done on the, on the the charged particle, right? By the field or by the external agent. So finally, let's look at the units. Because delta V is equals to delta U divided by Q naught, well, it's joules per coulomb. So 1 joules per coulomb is equal, defined to be 1 volt. And that's the unit for the potential. So the volt, you probably have seen that, right? So your, let's say appliances, most of the appliances at your home, are operated by using those AA, AAA batteries, which have 1.5 volt, which means that potential difference between positive and negative terminals is 1.5 volts. And also your, power outlets, right? They have 110 volts or 220 volts, depending, right? That means you have heard of that, you know, um, that quantity, volt. And here what we're saying is that volt is basically units for the potential, which is the volt is units for potential, and the change in potential or potential difference is then also known as voltage. Okay. All right. So then SI unit for the potential is volt. SI unit for the potential energy is joules. So that's why if you're doing, joules per coulomb, that's equivalent to volt. Now, since we're also saying that delta V, which is, this left side has a unit of volt, equals negative of integral of E dot ds. Well, what I can do here is, if I can rearrange this, right, I can see then technically then think like this. If electric field is constant, I can then remove that from the integral and just do integral of ds, which then gives me E times delta S, negative. Then electric field is then equals to then negative delta V over delta S, which is then volts per meters. And that's the unit for the electric field. That means there's another way we can represent units for the electric field. Remember, that means now we have two equations for electric field. Electric field is equals to electric force per unit test charge. That's where we got Newton per Coulomb. Now we're saying that electric field is also negative of delta V over delta S, which is volts per meter. It means how many volt difference we had during that, let's say, length difference. When object goes from point A to point B along the field, by how much the potential changed, and that's delta V over delta S. Volts per meter is also the unit for the electric field. All right, so generally when we consider electrons moving between points A and B and things like that, or electrons or protons, the energy that they gain or lose is extremely tiny. So maybe like, let's say 10 to the negative 20 joules or 10 to the negative 18 joules or something like that. And it's a very small number. And what we do here is we use electron volt as a unit of energy. So that's kind of like sometimes confusing for students. This says volt over there, so they think, okay, it has to be potential. But no, this is units of energy. So think like this. So if you have point A and point B like this, and if I'm looking at potential energy at point A is 0 volt, potential energy of point B here is then 1 volt. That means then your delta V is what? It's just, 1 minus 0, so it's 1 volt. That's your change in potential between points A and B. Then what is your potential energy, change in potential energy? Well, it's test particle times your delta V. Well, think like this. If this test particle happened to be an electron, remember electron has a charge of, let's say 1.6 times 10 to the negative 19 coulomb. All right, so let's say negative there, right? Doesn't matter. So then what I say is that it's 1.6 times 10 to the negative 19 times 1 volt, which is delta V. That means then delta U is equals to 1.6 times 10 to the negative 19 joules. Because what I did here, I did coulombs times volts. Coulombs times volt is joules. And that's what we do. That means when the energy is 1.6 times 10 to the negative 19 coulombs times volt, which is 1.6 times 10 to the negative 19 joules, which is amount of energy that this electron will gain or lose as it goes from point A to point B, where the potential difference between points A and B is only 1 volt, then we define that much energy as 1 electron volt. That means 1 electron volt is defined as 1.6 times 10 to the negative 19 joules. It's equals to exactly to that many joules. And it's a unit of energy and not potential. All right, so here's then kind of like summarizing everything that we kind of talked about. It's generally easier to understand how potential and electric field related if you have a uniform electric field. Obviously, uniform electric field means that electric field is constant, everywhere in this region. So then, for example, if you go from point A, here's your test particle, point A to point B, in the direction of electric field. So then this equation, remember this integral that relates potential difference between those 2 points to the electric field, allows us to see that if the electric field is uniform and constant, then dot product becomes E ds cosine of theta. Since this is the displacement, ds, and that this is the electric field direction, and they're in the same direction, theta is 0 degrees. So this integral just becomes E times ds. But if electric field is constant, I can remove that from the integral. Then delta V equals negative E integral of ds. Well, integral of ds is the simplest one we can have, and that's equals to just basically the length, right? The distance between A and B. Let's take that to be like distance d. That means delta V is equals to negative E times d. As simple as that. That means I can, if I have the electric field and distance, I can calculate change in potential. If I have the change in potential and d, I can use that to calculate electric field magnitude. That means those two equations are simple enough to use, and we can see how those two quantities, right, change in potential and electric field, related to one another. Also, you can see then, as I mentioned, right, if you're going from point A to point B in the direction of electric field, your potential will always decrease. If you go in the opposite direction of electric field, your potential will always increase. And that's kind of what we have. So that's what we're talking about here. So suppose the test charge moves from A to B, the change in the potential energy of the charge field system is delta U equals Q naught times delta V. Okay. Well, because then delta V equals to negative E times D, you can also replace it like that. Okay. So the negative sign indicates that the electric potential at B is lower than at A. Okay. So this is B, this is A. B is always lower because when you go in the direction of electric field, your potential always lower. Then the electric field lines always point in the direction of the decreasing electric potential. Not necessarily potential energy, but decreasing potential. Okay. All right. Now, we can talk about a system of, let's say, charges. Okay. So let me kind of actually, show you one thing here. All right, so let's say you have a source charge and there's electric field. Again, easier to like represent this as an electric field line. Okay. So you can see, right, in a system consisting of a positive charge and an electric field, and when we talk about positive charge, we mean like, let's say, see, at this point, I don't even need to, draw that guy over there. So let's say there's electric field in this region like that. So if you bring a positive charge, positive test charge, okay. So what we have here is this. It says in a system consisting of a positive charge and an electric field, the electric potential energy of the system decreases when the charge moves in the direction of the field. Well, it should make sense, right? Going from point 1 to point 2, we know then delta V is negative. Why? Because, well, V1, V2, well, V2 is always going to be less than V1 because you're going in the direction of electric field. And since then delta U is equals to Q naught times delta V, if delta V is negative, delta U is negative, which means that potential energy decreases. Right, which means equivalently, the electric field does work on a positive charge when the charge moves in the direction of electric field. That means you can also say that, delta U is negative because change in potential is negative, delta V is negative, or because, let's say, we can say that when there's a force acting and there's a displacement, and then both of them are in the same direction, then work done by this conservative force is positive. And when work done is positive, delta U, remember, is negative. Potential energy will always decrease when the work done is positive. Okay. Now, a system consisting of a positive charge and an electric field loses electric potential energy when the charge moves in the direction of the field, and an electric field does work on a positive charge when the charge moves in the direction of the electric field. Okay. The charged particle gains then kinetic energy equal to the potential energy lost by the charge field system, as I mentioned, right? That's what we have. When you lose potential energy, you gain some amount of kinetic energy. Things a little bit change when you have a negative charge, right? If Q naught is negative, then delta U is positive. Because if this is your electric field, and let's say you have a 0.1, 0.2, but this time you have a negative test charge, so test charge is negative. Well, here's the thing. I place the test charge at 0.1. In which direction is the force acting on it? Think about it. In which direction is the force acting on a negative test charge? Well, remember, it has to be always opposite in the direction of electric field. This is the force. But we are technically moving this guy in this direction, right? Oops. Like in this direction. This is my displacement to the right. Then my force is to the left. Then I can, use this. If the work done by conservative force is negative, it is negative because displacement force 180-degree part, so the work done is negative, then delta U automatically should be then positive. If the work done is negative, delta U is positive. Okay, so that's what we have. That means negative charge when it goes in the direction of the electric field. When the negative charge goes in the direction of the electric field, its potential energy increases. Okay, well, the potential is still, same way, V1, V2. If you're comparing, V2 is less than V1. That means my delta V is still negative. So then how come the potential energy is positive? Well, because delta U is equals to, Q naught times delta V. But if my Q naught is negative, then delta U is equals to negative Q naught times delta V. So then it's negative means that if this is decreasing, this will increase because of that negative. Okay, so that's why going in the direction of electric field, you always decrease your potential, but not necessarily you decrease your potential energy. You decrease your potential energy only when your test particle is positive charge, but you increase your potential energy when your test particle is a negative charge. So you have to be careful there. This is always true. That means regardless what type of test particle you have, if you go in the direction of the electric field, your potential decreases. But depending on what type of test charge you have, your potential energy can either increase or decrease. Okay. So, and this is going to be sort of like, let's say a little more general, right? Delta V, but same idea. Because the idea here is this, right? You go from A to B or from A to C, doesn't matter, right? So the idea is that the difference here is in terms of, for you is going to be the same because B and C are on the same line. So like, let's say you're looking that technically you are, this is let's say VA, and then you have then VB is the same as VC, and as long as VA and VB is the same as VC, doesn't matter if you're going from A to B or A to C, your delta V is going to be exactly the same. Okay, so your delta, you can write points B and C are at the same electric potential. They're exactly at the same electric potential. That means it doesn't matter which one you go, you can have exactly same change in potential, exactly same change in potential energy. That's why electric or the potential energy is path independent, right? When the field is doing work, is path independent. All points in a plane perpendicular to the uniform electric field are at the same electric potential. This is known as equipotential surface. Okay, so we're going to do a nice lab on this, equipotential surfaces. That means we will be able to find, like the name can suggest, equal potential. It means surfaces where the potential is all exactly the same. And then we can always use them to find the electric field because there's a very important, connection between them. So any type of equipotential surfaces, right? Because the equipotential surfaces associated with the uniform electric field consists of a family of parallel planes that are perpendicular to the field. That means, for example, let's do it over here. If I have, let's say, some kind of, a particle, source charge, uh, like this. See, if I chose some point P, like this, point P, which is distance r, find the potential. This is kq over r. Sometimes this is how I do potential, kq over r. Well, how about if I choose this point, P prime, which is, let's say, same distance, but in a different direction? Well, I'm going to calculate same potential. How about this one? Well, if it's same distance, same potential. That means I can kind of go and do like a circle like this. And if the circle has exactly same distance, right? So let's say, then potential is the same on that circle. Even if that's a sphere, three-dimensional, they have exactly same potential. That means I can go like this, all right? So here's another surface, and there's another surface. That means those are all have exactly same potential. Well, didn't work out that well. So let's say I was trying to do a nice circle, but let's say they will have the same potential. Those are known as equipotential surfaces. That means this will be V1, V2, V3, and I can look at in terms of, they all have the same potential here. V2 is everywhere the same right here. V3 is everywhere same right there. And those are known as equipotential. Electric field then will always has to be perpendicular to the equipotential lines, regardless of what it is. So if there's electric field, equipotential, they have to be perpendicular to one another. All right, so that's kind of what we have. All right, so let's look at then a few examples. All right, the facing surfaces of two large parallel conducting plates separated by 10 centimeters have uniform surface charge densities that are equal in magnitude but opposite in sign. The difference in potential between the plates is 500 volts. Is the positive or the negative plate at the higher potential? What is the magnitude of electric field between the plates? An electron, if then an electron is released from rest next to the negatively charged surface, find the work done by the electric field on the electron as the electron moves from the release point to the positive plate. Express your answer in both electron volts and joules. Then what we want to do is what is the change in potential energy of the electron when it moves from the release point to the positive plate, and what is the kinetic energy when it reaches the positive plate. All right. The thing is here is this, right? So we have two conducting plates. One is going to be positive, the other one is going to be negative, separated by distance 10 centimeter, and have a potential difference of 500 volts. So that means we can draw them like this, right? So here's, those are two plates. So let's say then one is positive. The other one here is then negative. Okay. Then what we have here is this. So this is generally can be used to, let's say represent those parallel plates, right? Parallel plate, you can see, right? So it says 500 volts potential difference. Now this could be, this is 1000, this is 500, or maybe this is 501, this is, if this is 1, doesn't matter, right? As long as the difference between them is 500. So then why not take this one to be 0 and this one 500, and then that's a potential difference of 500. And that's generally what we do. Usually we use a battery where, some kind of battery that has a positive terminal, negative terminal. When you connect the positive to the positive terminal, so that means this is 500 volts and this is 0. That means the one plate has the same potential as the negative terminal, so 0. The other one, plate has the same terminal, has same potential as the positive terminal, in this case 500. That means that's why we have the top plate is 500, which is the positive plate. The bottom plate, which is negative, then has potential of 0. And remember, then electric field always goes from positive to negative, right? So electric field always goes from positive to negative. That means in this region, we're also going to have a electric field, generally in this direction like this. All right. Now, our question then basically starts by asking us to, let's say, to find, says, is it positive or negative plate at the higher potential? So I just answered that, right? Positive plate is at the higher potential. Then it says, what is the magnitude of the electric field between the plates? Well, I have the distance between the plates, right? So then distance, remember, was given as zero point 0.1 meters. And I have potential difference between the plates, 500 volts. Then I can say that delta V is equal to negative integral of E dot ds. Well, it's negative, well, going from, let's say, 0.1 to 0.2, taking this to be 0.1, let's say this is 0.2, doesn't matter, right? So basically one plate to another. Well, think like this, electric field here is always uniform. That's one of the things about this parallel plate. When you have a two parallel conducting plates, electric field, it generates generally somewhere in the middle, right, is fairly uniform. So then it just becomes EDS. Well, which means I can remove electric field. So just have ds, and then this is just negative E delta S. Well, delta S is just nothing but your D. That means then electric field is equals to negative delta V over D. And it's asking for the magnitude. So I can just put absolute value. So I can say it's delta V over D. Well, delta V is 500 volts. D is 0.1 meters, right? So then I can calculate this, then get the, potential, electric field magnitude. Basically, it's like 500 divided by zero point 0.1 gives us 5,000 volts per meter. Okay, so you can write as 5 kilovolts per meter. Okay, so this is part B. Part C was asking then, let's say you take an electron, place it at the negative charge, surface. That means, take an electron and place it here. Well, we know then as soon as I place the electron over there, it's going to be repelled by the negative plate, attracted to the positive plate. So it's going to be pretty much, starting from rest, it's going to be launched toward the positive plate. That means it's going to go from this point. We're going to take this as 0.1. Right, so we're going to then take this as 0.1 to here is 0.2. Okay, from 0.1 to 0.2. So it says it's going to be released from rest next to negatively charged surface. Find the work done by the electric field on the electron as the electron moves from the release point to the positive plate. Express your answer in both electron volts and joules. Okay. Now, one thing we have here is then, well, there's that integral, right, for the work done. But here's the thing, we don't need any of that because work done, we just learned, right, is just Q times delta V. Well, Q naught times delta V. Well, what is Q naught? Well, it's an electron. What is delta V? What's the potential difference between the plates? That means this is equals to then 1.6 times 10 to the negative 19 coulomb, right? And times 500 volts, which is the potential difference. Well, since we are going from, let's say, from 0.1 to 0.2, remember, let's not forget the negative over there, right? Negative, 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 let's not forget those negatives. So because work done is equals to negative, right? Q naught times delta V. This pretty much what I'm doing is this. Work done by conservative force equals negative delta U, where delta U then replaced with the Q naught delta V. Okay, so that's what I have over here. So negative, negative is going to cancel out. So 1.6 times 10 to the negative 19 times 500, I get 8.01 times 10 to the negative 17 joules. But we want this to be represented in terms of joules and electron volts. So then I can say, all right, so where 1.6 times 10 to the negative 19 joules is equivalent to as 1 electron volt. If I calculate this, becomes 500 electron volt. So that's why you can see, right? This is a very tiny amount of energy if I represent it in terms of joules, but relatively more, compact and readable if it's in terms of electron volt. Electron volt is units of energy, not potential. All right, that means that's the amount of energy, right? That's the amount of work done, which is, then I can say that for part D, it says then, what is the change in potential energy of the electron when it moves from the release point? Well, this is the amount of work done. So the work done by the electric force is 500 electron volt. And I know this is then equal to negative of delta U, which means then delta U is equal to the negative 500 electron volt. Because, In this case, if the work done was positive, then potential energy then decreased. And in this case, potential energy decreased for the electron. Again, you can try to remember that in terms of in which direction the force was acting and things like that, right? Because the field did positive work, potential energy decreased. Right. So the last one then asking this: what is the kinetic energy when it reaches the positive plate? Well, I know one thing, that in terms of kinetic energy 1 plus potential energy 1 oops, equals then kinetic energy 2 plus potential energy 2. Or I can say, right, so then delta K plus delta U is equals to 0. So one thing I have is that then delta U is minus 500 electron volts. Well, then delta K has to be then plus 500 electron volt, so that, conservation of energy can work. And that's what we have. Delta K is equals to negative delta U, which means it's negative 500 electron volts. So delta K is equals to 500 electron volts. That's the amount of energy as a change in kinetic energy. All right, so here's another example. A uniform electric field that has a magnitude 2000 kilovolts per meter points in the positive x direction. What is the electric potential difference between the x equals 0 meter plane and the x equals 4 meter plane? A point particle that has a charge of plus 3 microcoulomb is released from rest at the origin. What is the change in the electric potential energy of the particle as it travels from x equals 0 meter plane to the x equals 4 meter plane? And last one is, what is the kinetic energy of the particle when it arrives at x equals 4 meter plane? All right, so let's see how we can solve this one. So we're given that there's a uniform electric field, which is, again, it's important, right? That means our calculation is simple, that integral becomes just E times D. Uniform electric field, it has a magnitude of 2000 volts per meter, or 2 kilovolts per meter, and in the positive x direction. That means I know in which direction is my electric field, like this, in the x direction. And it's uniform. So I can write it as, let's say, 2000 volts per meters I hat, where I hat is the horizontal direction. Then it says, all right, so what is the electric field potential difference between x equals 0 meter plane and x equals 4 meter? That means taking this to be the, let's say, the origin, I can describe this as like a plane like that. Okay. So I'm going to put it like this. It's like a plane, but looking from the side. And then here's another plane, x equals 4 meters. There's another plane. So what is the electric potential difference between x equals 0 meter plane and x equals 4 meter plane? Well, that means one thing I know here is my D is 4 meters, and my electric field is basically the 2000 volts per meter. Then if I'm calculating this, I can say, right, so then delta V for part A is equals to my potential at 4 meters minus my potential at 0 meters. This is equal to a negative of integral going from point, let's call this point A, and this point B, going from point A to B. Okay, this is like E dot dl. Okay, well, as I mentioned, right, so then my delta V is equals to, this is my delta V. Well, this becomes, uniform electric fields, which become E times dl. Can come out, then gives me then just dl, or negative E times, D or L, right? So, but this is what I have. Then my delta V is then negative 2000 volts per meters times 4 meters, which is the negative 8000 volts, because the meters cancel out. Negative 8000 volts means that there's a decrease in potential of 8000 as you go from A to B. Okay. It says then a point particle has a charge of plus 3 microcoulomb is then released from the origin. Okay. What is the change in the electric potential energy of the particle as it travels from x equals 0 to x equals 4 meters? Well, as you can see, right, to calculate potential, or change in potential, all I need is the electric field. To calculate potential energy, I do need a test particle. Otherwise, I cannot calculate that, because then delta U is equals to Q naught times delta V. That means it's a 3 times 10 to the negative 6 Coulomb, then times negative 8,000 volts. So I can calculate as negative 24 millijoules. That's now my change in potential. That's change in potential energy. Okay, so then the last one says, what is the kinetic energy of the particle when it arrives at x equals 4-meter plane? That means, what I have here is this then. I can come back here. So, okay, so then delta K plus delta U equals 0. That means Ka plus Ua equals Kb plus Ub. Okay, or I can just basically do it in terms of this, right? So that's the general, like a sort of general equation. But one thing I have is this. Delta K is equals to negative delta U from directly this equation, which is negative 24 millijoules, which means my delta K is 24 millijoules. Okay. Now, here I could have just then asked you another thing. So let's say if the particle, started from rest and moved, because we can see, right, there's a gain of potential kinetic energy. There's a gain of kinetic energy, which means that the object increased kinetic energy. Whatever speed it had in the beginning, now it has a higher speed. So for example, let's say at point A and point B like this, right? So let's say the speed at A was 0, which means then let's say delta K is equals to 24 millijoules, and delta K is Kb minus Ka. Let's say if speed was 0 in the beginning, then Ka was 0. That means Kb is equals to 24 millijoules. Now, what can I do with this? Well, I can calculate then when it gained this much energy as a kinetic energy, what will be the speed? I can say then 1/2 mvb squared equals 24 millijoules. Then Vb is equals to 2 times 24 millijoules divided by the mass and the square root. All I need to know is what is the mass of that particle, right? And I could then calculate the speed. If I knew that this was, let's say, an electron or a proton, which it wasn't, right? Or if I was given the mass, I could have calculated what is the speed at point B. That means you can always use this equation or that equation, right, to calculate the speed of a particle whenever, let's say, you're given um, change in potential energy. You can always relate that to the change in kinetic energy.